So the AtCoder Beginner Contest just starts. Let's try to solve it. I almost was late for the contest. Let me. There are often people. The string the ith person is found as a male, female, determine whether are alternating. That's kind of an interesting problem because it's now like gender things and shit like that. So when you now say in these problems you have male and female, you're gonna get a lot of hate. But actually I agree with the problem statement, so yeah. So if they're alternating, if so like this, if s is not equal s of I minus, if it is equal, then okay, it's false. That's pretty funny. That's pretty funny. Chessboard. Alright, so we have some chessboard, and what is this? So we have to just add this character. So we have to find where this star is actually. Okay. That's pretty okay problem. Okay, this is how we offset to what row, what column we are, and then what row we are. Okay, so j plus 1, or actually no, a is j, so this is j, so this is plus j, and this is I plus 1 as far as 8 minus I minus you were given some sequence, determine whether there is a pair ij such that this is the case. It's a known problem. We have to just rearrange the equation to get ij. Ij will be equal to x ai minus x. Okay, we got accepted on A and B. Okay, then we have a map. then we say okay, map map at AI minus x. So we need AI minus x plus plus if map at AI right, if map at AI cout yes return, otherwise cout no. Okay, that seems to be working. So we first add into the frequency and then we try this. That seems to be passing. Okay. Given positive integers n and m, find the smallest positive integer x satisfies both the condition of print minus 1. X can be represented as the product of two integers a and b between 1 and n. Okay. Is at least m. X is at least m. So x is bigger or equal than m and can be also represented with two integers from 1 to n. So this is something to do with the square root, I'm guessing. What is the third case? The third case is the smallest positive yeah, we just need to go to the square root of no, not really to the square root of n, like to 10 to the 6 probably, right? Because after 10 to the 6 times 10 to the 6 there will be like, yeah, so this is fixed 10 to the 6 on every case, no matter what you do. This is like A, and then B is going to be represented as this is A, and then B will be represented as m divided by a we're gonna try here something like offset then we're going to try like this. If b plus offset is smaller or equal to n, b plus offset is bigger or equal to n, is smaller than equal to n, and if b times a is bigger or equal to m, then we of course what should be the output? The output should be b times a. Or maybe it cannot be, so what is this now? 7 cannot be represented as a product of 2. This should be correct. Let's see. Okay, gets accepted. You're given a sequence of n integers. Here it satisfies that. Okay, we'll play n rounds of the game. The ith game will be played as follows. Specifies a positive integer ki after knowing ki. Aoki has specified Takahashi chooses an integer si and writes it. Repeat the following ki times. Replace the integer x with the. So it's like, okay, a cycle. So you're given a permutation. Aoki chooses some length where this can repeat, then Takahashi chooses some integer that where to start. Okay, so it's a game theory. Okay, this is solvable. This is solvable. Just have to I just have to okay, so we have some cycles, and each cycle I can to Takahashi to win the ith round, it has to end up being I no matter So no matter what integer ki Aoki chooses, Takahashi has to have a starting position where after this ki, so okay, Takahashi, I'm pretty certain that Takahashi can win every time except when? When can Aoki even win? First round, Takahashi chooses K1 to be 2, cannot reach whatever option he chooses. Oh, so it's not actually So it's not actually a permutation. It's a kind of I see. It's kind of just directed graph, right? Okay, it's not a permutation. That's what makes it difficult. Okay. Okay, if it's not a permutation, then something should possibly happen. So if I know if there is a cycle somewhere, in this cycle Takahashi wins, like any of these Takahashi wins. If there is a dead end where you have so anything that ends up in this cycle is like Takahashi wins. Okay, so we don't care about something ending up in a cycle. We care if there is something that doesn't end in a cycle. So we care if there is something like that. And then Aoki can choose an integer ki, which is probably way bigger than this. Two, 2, 3. So if he chooses S1, we go to 2 once, and then we go to 2 once. So I think that's pretty straightforward, but the test cases are really weak to just confirm my theory. Let me just code it and see where we are. So if it's already here visited, then we say if the components here is equal to my ID, then we say cycle is true. We break in either case. We say here is AI here, except that we need to do this. Okay, and then we say here's AI here, current pushback, current pushback here. Okay, so if I find a cycle, then for each element in the current, set answer at that element is 1. Okay, if it's a cycle, so we also need to say component here is ID, right? And we also need to ID++. Yeah, so the problem is now that, okay, if I start at some so I detect the cycle, but I have entered the cycle somewhere, right? So like it's essentially in each, so essentially it's like strongly connected components, isn't it? Isn't it actually strongly connected components? Imagine you have something like this. Okay, and like let's now imagine we have something like this. Okay, this here is a strongly connected component, right? These here are all strongly connected components. How do we do this? I mean, Takahashi can in all of these, in like this cycle, Takahashi can win all of these. But to win this, Aoki will just say like a really big positive integer, and you would never really win this, right? Unless it's included in a cycle. So essentially you want to cycle detect this, but you want to exclude these, right? So yeah, it's some kind of it's strong connect components, but let me just see without strong connect components. I can have another node here pointing to this node, let's say. So here, when I add a cycle here, I will actually say, okay, components in here. If it's a cycle, if element is equal to start, then true. Start. If s is true, then do this. I think that should kind of work. I don't think it should be that it should be the other way around. That seems to be passing cases. Yeah, accepted. Okay. Polygon and points. Let's see. Let's simultaneous swap is probably okay. I will just I want to see this here because geometry problems. I really love geometry problems. This is there is a convex hexagon in two-dimensional space. The vertices in clockwise order. For each query, answer the following: is the point inside or outside the boundary of S? This is a very well-known problem. Points in polygon problem. Points in hole problem. Yes, this could be it. Determine whether a point T lies inside clockwise with no collinear points. Turns true if I even had one other better solution here. Points in point in hole. Let me see. Let me see if there is already a solution that. No, I will actually use this solution here just for practice, because this is so determine. Okay, so but this says it's like in, out, and on the boundary. If it's on the boundary, yes. Okay, determine whether a point T lies inside the convex hole with no collinear. It's not guaranteed that there won't be a collinear points, right? Okay, there are. It's strictly convex. Okay, so this should work. This should work. I just need to figure out how to check if it's on the boundary. That's one thing I need to figure out. Side off on segment. Where is this side off? Calculate the area. Side off on segment. Okay, and I need point. I need point in whole. Point. I think I already had that templated. Okay. I need now type def point p. Define that. Wait, type def point p, right? Just do it. Essentially like this. I can just do this, right? Type empty. Okay, that's the same. I'll define here. The same, I need to define size. Also, I need to define, okay, side off, I'll clear that out. Let's just enter the points. I can use probably longs, right? Yeah. Longs, okay, points, tie.x, points, i.y. Queries. Point p, px, py. And now we have to query this. Now the problem is, does it lie on a segment? What is this R here? Oh, so if it's strict, yeah. So it says like return true if point lies within a hole. If it's strict, true points on the boundary aren't included. So if it's true, we have to check. So if it's false, we have to check So yeah, here LL cross, if cross is 0, then I will return on boundary, right? That was on boundary, right? Transfer string here. If it's otherwise, I will return if it's smaller, then it's true, so it means like it's in and out. And here I have to also say, okay, if it's bigger than R or if it's smaller. So this is if it's outside, probably. So R is not strict, right? If it's strict, this is false, it's outside, right? No, we want strict is false. First we want strict is false, right? Because false will give us that it can be on the boundary itself, right? This is if it's outside. If it's false, then this is true. This is outside. I think this should be the case. Okay, sign is not defined. Sign is a function where sign is this function, right? What else is not defined? All segment is not defined. Don't I have the on segment function? Oh, here return if it's R, if it's smaller than 3, then if it's strict, if it's strict is false, that's here. Like if it's on this segment, it's lies turn on, else return yeah, if it's like 2, but that can't be it. That can never happen. So okay, what about the sign function now? What's this? What am I seeing here? Sign was not declared in the scope. Oh. Okay, so we are here outputting out, that's correct. We're outputting somewhere in, or should be on, right? So if the cross product, so what's the cross product up here? 3. The counterclockwise order. Okay. We're outputting in. Here we got one counterclockwise order. So what is this -1, 3? Can we see this is -1, 3? This is on the boundary. And this C out LA, C out B. -2, 2 and -1, 1. Yeah, this is this line here, but maybe it's like this, so we have to check this. Okay, so LA. So I will check offset from -2 to like 2. I will check A minus A plus I plus size of L plus N divided by N. Just check it like this. That's new A. New B is B plus I plus N divided by N, right? And then you say that if on segment L and A, on segment is how it's defined. Start end per point. Okay, so L and B per point P. If it's on segment, then return on. Otherwise, this. That should be correct. Let's see. Okay, that's the wrong answer. Probably here with the on stuff. Two wrong answers, only 2 wrong answers. If the cross product is 0, wait, if the cross product is 0 but A not lie on the point, that's why you cannot just check it like this. You have to check it. I see. This is where the point is. It's like lies on the lies on the line, but actually it's not on the segment. because the dot product does not work. I think that should be correct though. I don't know. No, that's not correct either. Well, how is that not correct though? It didn't change anything. Site is bigger equal than R. It's like out. That's true. That's one. It's bigger than it. So it's like of course, what am I doing here? L to C is not a segment though. Just we're taking a look at the line, and then when we find this cross L to B, right? This is point in the call determines return true if point is in the call. If it's I don't know if that's even stress tested, but let's submit it once again without this joking aside. Let's just put 3 here as a constant time won't matter. That seems to be passing. So that was the mistake of like, yeah, that was the mistake of thinking this is correct. Yeah, okay, I see. Okay, let's solve F now. You're given 2 sequences A and B. It can repeat the following operation a number of times. Choose 3 paired distinct ijk. Swap ijth elements and swap I and kth elements. Is there a way to repeat to make equal? This is some kind of a flow problem or matching problem, something in this idea. Let's just, okay, let's see. Okay, let me just, let's just see the standings, my submissions. Also, let's read EX just so we have fun. Okay, we're 23rd place, which is pretty good actually. We have a grid with N and M columns where each square is painted black or white. Here at least one square is painted black. The initial grid of length M, so for like M, okay. Hikashi wants to repaint white squares, possibly black, so that the squares painted black are connected. Find the minimum number he needs to repaint to achieve his yeah. So we have some things like that, and now we have to paint some squares to connect these. This also looks like some kind of a flow problem. How do we connect this most optimal? Like, it's weird that 7 here is this, like 2 to the 7 is 128, so 128 combinations we have for each layer, and if each layer is painted we can match 128 combinations. So is it a DP problem? Like 100 layers, each match 128 possible from this layer to this layer, while some of them are actually this, and then you just is that simple problem? Is it that simple? Just we need just the previous layer, right? So we need like a DP where we need a vector of like 2 to the 2 to the M numbers. Right, and then the first layer to match, like, so first we're gonna do like this base case where I'm going to iterate through all of these, and then I will say that okay, so first we need to say if it's a valid configuration. So I will just do maybe a function here where you accept layer and then configuration, and then you say that, okay, to be a valid configuration it means to have, so for each number for each M we have to, if config and IM is true, then we have to also, then it has to also be true if this is true, then also lay A at, no, if A at layer is true, and this is false, then this is not valid. So if this is true and this is not the layer at I, right? If there is this, then it has to have like that. If there is no like this, then it just doesn't make sense to have like this. I mean, it doesn't mean that it can be either way, right? So that's possibly correct. So return OK in here. And then I will say if is valid configuration and so for each of these layers, so this is the first layer, actually this is base case. So for the base case, if it's valid layer 0 to have I, then we say that the dp of I is the count at the first layer minus the built-in pop count of I, right? Okay, that I think is correct. Now I will just add a vector here. If a at ij is this, then count at I plus plus. Okay, this is fine. Then for each other layer, except that the trick here is that how do we know that they're connected? Oh, there could be something like that. So there could be something like that. I see. Okay, I see an edge case here. I see an edge case here that I have to think about. Maybe it's some kind of data structure. But let me just focus on problem F maybe, just because I think I have seen something like this before. Okay, so they're these integers, and there you can swap I and the jth element and swap I and the kth element from B, right? So what does it happen here? So this is AI, this is AJ, and this is BI, and this is BJ, right? Right? And now what you can do is you can this element with this element swap, because like when you put this element here and when you put this element here, these elements do match, right? So yeah, so this problem is very well known, I think. I mean, let me just check. Code forces. This is problem F. This is some kind of problem. Problem F, code forces. Problem F, match flow. This is a known problem. Problem F. Traveling bounce ball. It was some kind of think just to get this, I'm pretty sure it's a flow problem. Graph coloring, range on the double sort, that's the problem. Let x be an integer, y swap AI, and this swap this, permutation and sort it in ascending order. And this is okay. This is the 3000. What is this? This is 212. Then okay. So when you swap these two, they have to be equal. So you can only swap equal elements. So you can only swap like equal elements. I mean that makes sense. That makes sense, right? To take two elements and swap them with some other two elements, right? So it has to be a flow problem. It has to be like some kind of bipartite matching problem, I would assume. Because you would connect these two elements here, right? And then you would say that, okay, you would connect these two elements. Now let's imagine that you will swap them Let's imagine that you would swap them first with some other here elements, right? No, first you swap them like this, right here. And then you take, so this guy here comes here, right? And this guy comes here. And then you have to somehow match this. You can swap this guy with this is some kind of bipartite matching, I'm pretty sure. So let me take a look at this here problem. This was like the operation. But yeah, the problem is because of the 10 to the... Because 10 to the 5, you cannot just do bipartite matchings with... So it really depends on the edges. If there are n edges, then... I don't know, really, like... Let me clarifications. So what's the idea here? I'm pretty sure this is an easy problem. I'm just overcomplicating it. Because I've seen this thing with the permutations. So when I swap these two elements here, this here guy has to somehow then match with this here guy, and this here guy has to somehow match with this here guy, right? So let's see like this. So let's see that the count of like the frequency arrays of all of these are the same. Okay, this is not the same here. You cannot do this, but let's see. Yeah, this is like, so this is frequency count is the same. This probably frequency count should be the same. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is pretty much counted the same. And now they claim this is impossible. Why? So if you want to order the ones, right, you could probably reverse these operations, right? Like you could take a look at them as a way of can I choose I and j to be equal elements? Is this possible? Choose 3 pairwise distinct. Okay, pairwise distinct. So I cannot choose that. So let's say that. Okay, so let's say that I choose. There's something to do with the cycles here. There's something to do with the cycles. I'm pretty sure. Okay, let's draw this permutation and see what we can learn from it. 1, 2, 3, 4, 5, 6, then 7, 8, 5, 6, 4, 3, 1, 2. Okay, let's see. So 1 and 1 is connected like this, right? They have to correct. We have to. If I find another place here, and then I connect these two, I can just swap the 2 here and the 8 here, let's say. Right? So 2 and 2 are connected like this. 3 and 3 are connected like this. 4 and 4 are connected like this. 5 and 5 here. So let's just somehow make this better and better to understand this. No, you can't see it here 1 and 2, but like it's fine. So 1 and 2 are like this, right? 3, 4, 5, 6, 7, and 8. So if I somehow be able to so if I pick this here, right, what will happen if I pick this call to be one of the ones to be one here? So here you are swapping 1, and here you're swapping 8, right? So here's a 2, here's 1. And then you cannot use this column anymore. So let's put 2's here. So we're just going to say that 5 and 2 are going to be swapped. 2 and 3 are going to be swapped. So you could potentially do that for all pairs, and at the end you will be left with 2 things here like unchecked or something. when you do for this for all columns, there will be like two unchecked here. And by these two, it actually like depends everything everything else, right? So how do you check if these two actually also mean, and then I'll do this. How do you check what when the pair is left? Does it matter? Does it matter? That's my question. That's my question. Does it matter? This ex unite, this is kind of cool problem, because like I think the DP should work. So the edge case in the so the edge case in the unite problem is the following. Somehow you have some configuration like this, and then something like this, and then you probably want to fill in these here. So let me just draw it another color. You want to fill in these here. Instead of just doing something like this. And okay, this is kind of cool. Essentially, what you don't want to do is like have a village of some things, and then you have like another thing like this. This is what you don't want to do. It's what you can't do. So you could possibly leave like this, right? But the next guy has to all of these islands has to cover it somehow. Okay. So this is DPI. This DPI plus 1 has to cover all of these islands, like regardless of yeah, something like that, something like that. So the base case is fine, like this is the base case. So the base case is kind of fine. Whoops. Because we go all, and if it is valid, it's just okay, it's fine. Right? But then for each of these, I have to first go for each of the configurations. And say that if it's a valid configuration for the ith row. So if it's not a valid configuration, I'll just skip. Okay. So now if it's a valid configuration, I want to go for all of the previous configurations not a valid previous configuration for the I-1 row, so this is the CP. If that's not valid, we're just going to continue. Now we have two configurations. One is the config and the other is the previous config. Okay. Now we need to somehow merge them. And the merging process is saying that my config should fill all of the connected components in the others config. So can I have like a DSU for the other config, and then I would say like always just unnecessary memory, but so I'll do this. I would so if merge config and CP, so I will have like a maybe not a function. Let's just do it here. Merged. Bool okay is okay. So first I have to go into the vector and say visited previous is m, right? For each of my current m on the current config, visited previous. So I'll just add to a queue here. Visited previous. So if for my current, what happened here? Am I still recording? I think I am. So if current m and my config is true, then we're gonna push current m to the queue. We're gonna say visited previous is like add current m. Actually, we're gonna just push it to the queue. Then and I need to know that actually this is kind of worth doing. So the previous current m at the previous config is also true. So then I'm gonna push to the queue. Then while the queue is not empty, I will say out to top is queue.front queue.pop, and then I will say so I'll have dx here is if visited at visited brief at top, then just continue. If it's not, we say that visited at top is true. Then for the direction, the nx is what am I top plus the exit direction if this is valid. So if this is the case, then if it's not visited previous at top and the is not visited at nx and nx and the previous config has the bit in common, then we will say that q.push nx. Okay, so this is the case, and then I need to check is bool okay is true. Then I will iterate over the current m, and I'll say if current m has something in common with the previous config, and then visit the previous at current m is not true, then okay is false. And then when you do this, you say that, so what you do is you say that so this is, well, this is how you check it. We have the two configs this, okay, we merge this, we check if we can fill at least at all of them. Oh no, this is connected. Is it harder than what yeah, it's harder. It's like the DP is not only IJ, it's like, okay, what is being like the config, right? Okay, what is the config? But is it possible to be like each config having each of the 7 dimensions having multiple choices? Like, okay, well, what if we don't have that? What if it's like component 1, component 2, or component 3? Because if it's 7 places, so there's 7 places, right? What you can, in worst case scenario, have is this is a different component, this is a different component, so you have like 4 components, 4 different components. So technically you have 5 to the 7th, which is a lot, times 100, and then times 5 to the 7, like squared. It's just a lot. So yeah, so this is like this is the way how you will try to compress the state. Instead of having 5 different things that go down, 5 different 4 different components, you would probably in this case have 1 component. So what if really, like, how many components would you really have here at most? Let's say this and this is a component, and probably like these 2 can have, but this probably can be a component as well, right? So probably like 3 components. Let's say 4. Let's say that the complexity is 4 to the 7. Still, it's too big. So 4 to the 7 is too big, but 2 components is not that big. It's like 3 to the 7. Which still is like that squared and then times like 100 and times plus like 7 times 7 or something like that. It's probably right. If you have 2 components, you have to distinguish them. So somehow you have to distinguish them. Yeah, so instead of here like 1 shifted to this, it's like power 3 to the n, 3 to the m, right? So let's pre-compute this. And here is now no longer bit operations are possible because of this. It's, now no longer bit operations are possible. That kind of sucks. I need to so if there are 2 components, you go 2 components and then you have to kind of merge them into one, right? But what if there are 3 components? What if there are 3? What if first you start with like 3 components? It could be this way, right? Like, let's just see this case. You first start with 3 components, right? And then technically, actually, like, let's say that this is a little bit down, right? So yeah, you technically want to merge them as quickly as possible. Yeah, so you want to merge them as quickly as possible into at least like 2 components. I don't know how to prove that. I don't know how to prove that there could be only 2 components here. So if I really want to say like so you want to get the ith thing, so you want to divide this by specify this pi times, right? This is, if it's like, if I is 0, then you just do this, right? So here you want to get, so is it valid? It's valid if get at you get config I 0, then this is valid. Okay, this is fine. Here we're going to the limit of this, and here we're going also to the limit. Now we have to merge them. Oh, this is insane. What did I even do here? It's not even correct. It's not even correct. So it's like get cm from config is to see if that's valid. How to see if that's valid? So you're here somewhere, and you say this is config 3. Like this is 3. This is component 2 or whatever. Then can I somehow else implement this? Can I have like a DSU here for this, like having a DSU and saying, okay, these are my components? I can maybe even do it like better. I could say that the first component is always. I could say that the first component is always 1, and then the second component is always 2. The third component will never exist. But no, this is then we have to relate these structures. How to like brute forcefully do that? Let's say we have like really 2 components. So this is our base case, so which we need to fix actually, because a valid thing is not a valid thing if we have unconnected So if, especially in the base case, like in the base case, you have to be valid like this, but then there's like the connections. Connections. So the connections is you. Which place did I fall? Yeah, I have 3 minutes, which I won't solve this problem, but the connections are done. I can just check if yeah. So this is just implementation. I have a problem. What I need here to do is I need to check for the component 1 and the component 2. Okay, this is valid. This seems to be valid. This seems. Why are there not more of these? Oh, because we're going to n up to the limit of n. Okay, so these are all of the combinations that we can create. Okay, and now we have to check if all of the components are actually connected with which I won't have time to go, but I will just go over the problems really quickly. So the first couple of problems were easy, but I'm just gonna go. So is it alternating? You just check if they're different. The consecutive numbers are the consecutive things are characters are different, and it's false. Okay. It's no. Then here you just do the indexing. It's nothing. Here, see, you have to rearrange the formula, and you fill the map. And when you fill the map, then you have to ask for each of this. Is this integer inside the map? D, you just go to the square root, because square root times square root will give you m, and after that you just don't need to do anything like that. Transition game is just simple. If it's like in a cycle, it's definitely this guy wins, Takahashi. If it's outside the cycle, Aoki wins, no matter what Takahashi does. Polygon in whole, this is a known problem. It's it's a very known problem. Like you just binary search the you just binary search like rotating calipers, or was that the name? I'm not sure, but yeah, essentially we just fix here on like if it's on a segment. I just want to know if it's this, if I was correct about the simultaneous swap. Simultaneous, so it's just probably greedy. Okay, it's okay, he just sorts it and okay, there's some kind of fanfic tree. Yeah, counts the inversions or something. Okay, whatever. Just I'll ex 2 to the 7 ways to paint the bottommost column. At most 4 permutation states with connected component because adjacent. Okay, so four factorial states of the connected component because adjacent back squares same column belongs of the same. Yeah, okay, I see. Like adjacency will just yeah, that's what I said, but 4 factorial ways. Isn't it like 2 to the 4? No, actually no, it's 4 factorial. Okay, I mean okay. It's just really hard to implement. It's just really hard to implement. I think if I had like more time, maybe I could get this implementation with 3 to the 7 things, and I'm not sure even if it would pass. But I would need more time to code it. Yeah, thank you guys so much for watching, and I see you in the next one.